Okay, so let's go to the next problem. In this problem, you're given an array of strings words. By the way, don't look at this easy tag. I'm not sure why they marked this as easy. It's probably a medium question. Given an array of strings words representing an English dictionary, so it's a collection of English words. We want to return the longest word in words that can be built one character at a time by other words in words. For example, if your dictionary is storing all these words, you want to find the longest word in this collection that can be built one character at a time by other words in words. I think this is just a confusing way of saying that what is the longest word in this dictionary such that every prefix of that word also exists in the dictionary. So if you look at the output is world here, because world exists in the dictionary and every prefix of world also exists, like WORL, WOR, WOW. If the dictionary had been this, and if we had to find the longest word such that everything, you chop it to any extent you want, you will still get words in the dictionary. So apple is the answer because apple exists as a word in the dictionary. APPL exists, APP exists, AP exists, and A exists. Now, when there are multiple words that are equally long, like apply is as long as apple, we want to return the word. When there is a tie, we want to prefer the word that is smaller in lexicographical order. So we prefer apple over apply. And if there is no word that whose prefix exists, we return the empty string. And again, our words are all lowercase English letters. Okay, so let's think over this for a minute. Questions about the problem itself you can ask right now. Murli?
Yeah, so let's see if there was a word called ban.
Ban.
Yeah.
In which example?
In the second example, there was also an additional word called ban.
Okay.
Actually, technically, banana is the longest word in the tree, if you see.
Yeah, but BAN,
it doesn't have prefix, right?
Yeah, BANAN does not exist. Even if there was a word called ban,
yeah,
it would still not make banana the longest word because BANAN does not exist. BANA does not exist. BAN might exist, but not BA and B.
So
Every single prefix.
Okay. All prefixes should exist. Okay, got it.
Yeah. So when they say return the longest word in words that can be built one character at a time by other words in words.
Okay, makes sense. Yeah.
That's what they mean. Umesh?
Yeah, we can sort the words by length.
Oh, okay. So yeah, I'll just wait for 30 more seconds and then we can discuss. Okay. Yeah, Umesh. You said you would sort the words.
In the increasing order of their lengths, so that smaller length words will get first inserted into the trie. And while inserting the word, we will check each character if it is already present in the children of a current node. And then we can keep track of the global max. If the character is not present, that means this word cannot be created uh,
Yeah,
using.
yeah, but we would need to return the longest such word and break the tie by uh, picking the smallest one in lexicographical order. Also, so when you say sort, if there are n words, you will firstly take n log n time to do the sorting. And actually, it will be not just n log n because there's a string sorting. So you will actually, unless you do something like radix sort, you will end up taking more than more time than what might be needed for
Mhm.
uh, for a more for a faster in a faster solution.
Okay.
So we need to try to avoid sorting for that reason. So firstly, why would we build a trie? So we are given a collection of words, right? And we are asked a question about the longest word under the constraint that prefixes of that word have to also be present in that collection. And so since the trie data structure we have seen stores a collection of words and prefixes are easy to identify for any word in that data structure, we think in the direction of a trie. Now, instead of sorting, which will take n log n time, let's assume that we will need to insert these words in the order in which we find them. So any word of length d can be inserted in time order d, as we've seen before. So assume that we have built a trie. And because the words could come in any order, it's possible that longer words could be inserted before shorter words, which means that when we are inserting a word, at the time we are inserting that word, it's not necessary that all the prefixes of that word have already been inserted. So in the process of inserting that word, we might pass through a bunch of words, a bunch of nodes that are not end nodes. So what we essentially want in this problem is the longest path in the trie that consists purely of end nodes.
Yes, I
So
think.
whichever the word is that with the longest word that meets the criteria given here is also the longest path you can follow from the root, where all the nodes along the way are
End of end nodes.
also exist in the trie. So uh, now, since the trie was built in an arbitrary order, uh, you have no option other than to explore the whole trie. Right? Build the trie and then traverse the trie, keeping track of which is the longest path you've seen, um, composed purely of end nodes. Tal?
Yes, I think following what you said, can't I do a BFS, but I only insert to the BFS children that are also words? And if when I start adding things as I traverse with the BFS, I keep the longest word because I'm traversing from left to right. I'll always keep lexicographical order. I'll have to exhaust the whole tree. But if something is not a word, I just don't insert it in the BFS. So it's a modified BFS on that structure we defined before.
So you're
Something
saying BFS on the trie, breadth first search on the trie?
Yeah.
Yeah, that can work. Yeah. Uh, the space though might be more.
Oh,
The space required, since you would need a queue, you would need to store all the nodes at each level. At least
I
the
guess you
ones.
can do a DFS maybe and go
Yeah, I
that
mean either of
way.
them
And
should be
then
are correct, but DFS will
same
have
thing.
a
Yeah.
order D
Right.
space complexity in the
You're just not going
recursion.
down if you're not going down if it's not a word.
Yeah.
So, no.
Yeah, so we'll write the code for that. Questions about the algorithm? Sesha?
So, Omkar, sorry, I had just stepped away from my desk. So the thought process I had was, let's say you had WW all the way to world, and let's say we had another sequence, say water to water world. So the longest word was going to be water world, right?
So we need all prefixes to be present, not just the longest word. We need all
Oh,
prefixes of that word to also exist in the trie.
oh, okay.
Hengli?
Hi, hello. So I was thinking maybe using some augmented data structure, like for each node, it will, does it make sense to store the longest depths it has? Will this simplify the problem? But it still need to, if that's the case, you can just, whenever you insert like a new node, it will you can use like a stack to keep the parse, and then on each step you just return to its parent what's the depth right now. If this depth is larger than the existing depth, you just update that value so that in this case the root will contain like the longest depth of this trie. So in this case, after inserting all these words, you will know the answer just by looking at the root.
Yeah, so that will make each insertion more expensive though, because so for example, there can exist. So suppose we have a word that is inserted first like this, and then we have a prefix of that inserted like this. Then we have this word inserted like this. And then at some point, this word is also inserted. So when this word is inserted, we need to walk down and check. So I assume by depth you mean the depth up to which we can find a continuous path
Yes,
purely of end nodes.
yes. But
So-
in this, yes, go ahead.
But when you insert, when I insert a word that ends at this node, I would need to go further down, along every path rooted at this subtrie to figure out what that depth is for
Uh,
this node.
I do not think so, because at that node would store the longest depth.
Oh, okay.
Yes, you know that, so that when you insert it, you just return like the current depth, and that current depth is compared with the existing depth. So if that is current depth is larger than the existing depth, you just go upward, and then update all of this. So you can use like a stack to store like the parse from the root to the current node, but that requires modification of the tri node structure.
No. Yeah, I'm not sure I understood the details, but here when you insert this node, or sorry, this string, and this node becomes an end
Because
node, when it
yeah,
becomes an end node, what value are you going to give it? You look at its children to decide what the depth
yeah.
from here is.
If that's the end of that word, it means the depth of the current string of this word is 0. So and then if this one has depth that's larger than 0, you just check it's larger than 0, so you do nothing. And all the node like upstream, it will not be affected. So this insert process just stops it.
But why will these nodes not be affected? Because their depths will also change. If this becomes an end node.
Yeah, I only store the maximum depth from this current node. So if the insert,
When you say depth, you mean in this direction or in the
longest, I mean up downward from to the leaf node to the depth
okay,
the length to the longest
okay.
to the longest leaf node that has the longest path. That's what I refer to.
Well, so it doesn't have to be a leaf node. You mean the end node?
Yeah, or end node or leaf node. So one eastward node.
Okay, so the longest path in this subtree,
Yes.
which looks purely like a chain of end nodes. That is the depth of this node.
Yes, the maximum depth, or you can define it maybe just as depth. Does not matter.
Okay. Yeah, so then when you insert this value, you will look at the maximum for all the children and then add 1 to it.
Yeah.
Right. And then
I do.
then you have to go back up to the parent and update all these.
No, if I do not update the depth of the current node, I do not need to update its parent.
But the depth will change here, right? If this node becomes an end node, its depth by will increase, will now become some new value, right? So the depth was 0 up to this point because this node itself was not an end node.
Yes.
So now it's going to become non-zero. So you have to look at its children to decide what the new depth is. And
If
that has to be passed up because the depth of this parent also might change because previously the previous depth might have been along some other path here. Now it might become along path.
Yes, but the depth of the parent node just equals like 1 plus its
max of
this child node.
Yeah. So you can update it. It's just that you need to do it for for that node and all the ancestors going up.
The worst time is like each insert you will update it. So, but it's still like the time complexity will increase by a constant factor. For example, the length of the word to like two times the length of the word, and then you will need to use the stack to store this parse. But the time complexity, in the sense of time complexity, does not change.
Yeah, that's fine. I think this should work. So whenever you're inserting, you are basically using a space-time trade-off by saying, let me store the depths, pre-compute the depths with every insertion and keep those depths updated, and so that when it's time to actually compute the longest such word, it would be already there at the root.
Yes, right? That's right.
Yeah. The only other thing though is we are not just supposed to return the depth, we are supposed to return the longest word itself.
Okay.
So which means you will need to store strings everywhere.
Yes, that's
right.
More, if you need to store the longest word, that will be maybe more involved. I need to think more about it.
Yeah. But if this was just an integer value, then yeah.
Omkar, this is Sisha.
Yeah, just a minute, Sisha. I think there are a bunch of other hands also. Shobit?
Yeah, hi Omkar. So my question is kind of basic in the sense that whenever we get these string questions, specifically when we get list of strings, like the input is like list of strings and all, like we directly, what are the what are the hints from the question we get? Like for example, in this question, we directly jump to using try, and then when you said, when we were thinking about sorting and all, you said that it will take even more than n log n. So when do we have to think, like, okay, we have to consider the factor of length of the word as well in the time complexity part as well? So what are like, I'm trying to get an idea about that part, like specifically, like this is a try talk class, so we know that we have to use try. But we can, when we get a random question, what are the, like, how should we move ahead? Because even in Leetcode, they try to first do using hash map, and then they say they compare the time complexity, and then they move that, okay, try is the better approach. So I was just trying to understand how should we think and move in that direction.
So when you have prefixes, right? So in this problem, firstly, it's a collection of words.
Mm-hmm.
Now there are no. It's not a dynamically changing collection.
Mm-hmm.
It is kind of a static collection.
Mm-hmm.
And you're also, so the specification here is that you want the longest word that can be built from, earlier shorter prefixes.
Mm-hmm.
So you're looking at all the nested prefixes and saying that they all need to exist.
Okay.
So when you're looking at a word and all of its prefixes as something that exists in the collection, how would you know that that a word and all of its prefixes exists in a collection?
Okay, so you mean to say that we should always start thinking in terms of try whenever we get some sense that, okay, prefixes are involved.
Yeah.
Okay.
Although not so, we'll also look at the next problem where you'll see that there's something else there. But
Okay.
yeah, commonly when you're talking about collections of strings and you're looking, the problem is also referring to their prefixes, then a try is a natural thing. There could be problems where suffixes also might be involved, like for example, last time I talked about prefix queries, right, of the form APP star.
Mm-hmm.
Right, what are all the words that match this wildcard pattern, right? What are all the words that start with APP?
Okay.
If so, you can get that clearly from a try.
Okay, and immediately when we know that, okay, we have a hint that we have to use try. So in terms of time complexity, we should start thinking about using the length of the string as a one of the.
Some, because it's radix. So try is built on the principle of radix search. So that means you have to look at the lengths, the internal lengths of each string.
Okay. Okay.
So the size of the try would, in the worst case, be order n times d, where
Okay.
or you can say sum of the lengths of all the words.
Okay. Okay. Thanks.
Now, having said that, there could be also queries of the form star followed by some suffix.
Mm-hmm.
How do you answer queries of this form, where you want all words that end with ion, not begin with some prefix, but end with some suffix? Now, even for suffixes, so these two queries they look kind of symmetrical. So what you can think of doing is to take that original collection of words and build a try on their reverse. So take each string and build a try starting from the right end instead of the left end.
Mm-hmm.
So when you do that, you get essentially instead of a prefix tree, you get uh, something like a suffix tree, although that word suffix tree is used for in a slightly different way, but roughly speaking, you're storing a collection of words by using suffixes as the way to access them. So to answer a query like star followed by ION, I would actually start from the root and then go in a right to left direction, NOI, right? And wherever that suffix ends, NOI, whatever node I'm at, all the words that are below that node have or end with ION as the suffix.
Okay.
So it's like a symmetrical tree to this prefix tree.
Okay.
And so you can answer these kinds of wildcard queries also. And then if you had another type of query like IN star ION, right, a single wildcard like this, then you can express this as all the words that have IN as a prefix and all the words that have ION as suffix.
Mhm.
So you can think here in terms of building two trees, a prefix tree and a suffix tree, and then searching for IN, the prefix IN, collecting all the words that have that as a prefix, searching for the suffix ION, collecting all the words that have that as a suffix, and then taking their intersection.
Okay. So
And then going to the postings list for their intersection and then taking the OR of all those postings lists.
okay, so basically primarily if it is a suffix or prefix, then we should go in that direction. But if it is some other problem, then probably we should first think, is it a general hash table problem or not, and not just jump directly to try or something, right? If the problem is something different.
Yeah, so one example of I don't know if I have a cheat sheet.
Yeah, okay.
I don't think I have a cheat sheet here, but uh, problems about prefixes or suffixes make us think in the direction of transform and conquer approach, and taking a collection and transforming that collection and storing them in the form of a trie is something that's allowing efficient future searches on not just exact matches but also prefix and suffix searches.
Okay. Thanks, Omkar.
One thing that you can't do here obviously is if I have ABC star DEF star HIJ, something like that, this can't be done easily, because if I choose this as the prefix, this as the suffix, that itself won't give me all the words taking the intersection of these, because we also need an intermediate substring to exist in the word. So anyway, so that's one of the limitations. We are talking about prefixes and suffixes, not internal substrings.
Okay. Okay. Thanks, Omkar.
Okay, so getting back to where we were here, so we want to return the longest word that exists in the trie, where the path from the root to that word is composed purely of end nodes. So after building the trie, we can just traverse the trie, keeping track of the longest path with end nodes that we have seen as we traverse the trie. Maybe using depth first search, since the space complexity with DFS won't exceed order D, where D is the length of the maximum word. So let's go in that direction and see how to write the code for it. So we'll assume that again we are using a basic trie, because here the words are not present in multiple copies. It's just a set. So it's a set. So that means we can go with a class definition of a trie node where we have a Boolean end value and a hash map, which is collection of key value pairs, which we'll just call by the name children. This is initialized by default to an empty dictionary. This is initialized by default to false. So assuming that same basic definition, we can write the code for this problem by creating an empty trie and then inserting all the words in the dictionary into that trie. Okay, so this is the transform part where we go through each word in the collection of words, the dictionary, and insert the word into the trie. How do we insert the word into the trie? We just reuse the earlier code, start from the root, and then you have a variable that goes through every character of the word, and we check if the ith character of that word is not already a key, does not already exist in the hash table in current.children. We will create a key value pair there in the hash table where the key is going to be word of I and the value associated with that key is going to be a new trie node. And having created that, we go down to that child. Could be newly created child or an existing child. So when the for loop ends, we would be at a node that marks the endpoint of the word that we were trying to insert. So we would mark that node as an end node wherever we ended. And that would lead to the creation of the trie. So notice that we have multiple insertions happening inside an outer for loop here. So it's the same code, but it appears inside an outer for loop since we are inserting every word in that collection of words. So this builds the trie. And now we need to traverse the trie. Now we need to traverse the trie to extract the longest word. Longest word which meets the, meeting the constraints. And the traversal method we'll use is depth first search because of the space, the relative space efficiency it has compared to breadth first search. Now this depth first search is going to be a top-down depth first search, because if you imagine being given this tree structure and you're asked to find the longest path composed of end nodes from the root down to the, to all the nodes, you can imagine, a waterfall model where, information is flowing purely in a top-down way, and you should be able to detect, even if nothing was coming back up, which is the longest such path, assuming that there is a global mailbox out there which all the nodes have access to. Every time a node sees that the path down to me is longer than what the mailbox, the global mailbox outside has, I can update that longest path. So we've done this, in the trees class. I think even in the recursion class, the template is the same for a top-down approach. So that's what we'll use. One small thing to keep in mind here is that when we say all the prefixes have to exist, the root node itself is an empty string, corresponds to the empty string. And normally we don't treat the root node as an end node because we think about non-empty strings existing in the trie. But for the purpose of this definition of what we are given here, that all possible prefixes have to exist, it would make it easier in our code to have the root node also be an end node, so that if there is no such longest path, then the root node itself will be the longest path. And since the root node corresponds to the empty string, we are actually given here that if there's no answer, we need to return the empty string. So for that reason, it would make sense to just add here a small tweak saying that we are treating the root node as an empty prefix that exists in the trie. Anyway, so we'll follow the same depth first search approach where we're going to write this recursively, which means we have to write this from the perspective of an arbitrary node in an imaginary corporate hierarchy. So imagine the root manager is given the task of finding the longest longest path in the trie. So what will the manager do? The manager will look at how many children the root node has. For each child, he or she will hire someone else under them to figure out what's the longest path in each of those subtrees under them. So what's the longest path here? What's the longest path in this subtrie? What's the longest path in this subtrie, and so on. And since we are doing this in a top-down way, we will assume that the path so far that has been detected is going to be told or passed down to them. So what they have to do is to figure out what's the longest path in my subtree and then take the path from the root up to that point and just prefix it to that longest path. That will be the longest path there. And since everyone is getting this information from above, it makes sense to pass it down a slate. So that's like our partial solution which is being passed down. The subproblem definition is basically the root node that we are given for that subtree or subtrie. So if we were to think of writing the code from the perspective of an arbitrary manager in the hierarchy, the subproblem definition is the root of some subtree that we are given. We have to find the longest path in the subtree rooted at this node, and the partial solution might be passed down to us on a slate. Okay. Partial solution, subproblem definition. Now, each node in this tree is, so let's think about a leaf node first. What is a leaf node going to do? A leaf node in this tree is lying at the bottom somewhere in the bottom layer. The leaf node is going to get a, if at all the leaf node is called, that means there was a path from the root up to the parent of that leaf node, which was composed purely of end nodes. And the leaf node is asked to figure out the longest path in its subtree. So the leaf node is going to not have any children, and so what the leaf node has to do is to take whatever is on the slate and check whether the path on this written on the slate is better than the longest path that has been found so far. And if so, just go to that global mailbox and update the longest string that's there. And return, right? No further delegation needed. For an internal node is also going to receive something from the slate above, from the manager above on the slate. And if the internal node is an end node, then the internal node is going to take what is on the slate and again see if the path up to it is longer than the best path that has been constructed, so found so far, and if so, update it. And then, depending on how many children it has, it will hire as many people under it as needed to then pass this information down to them. So at least some part of the work seems to be common to leaf nodes and internal nodes, which is that they're going to take the partial solution from their manager, look at whether they are an end node. If they are an end node, that means the last letter that was added by the manager on the slate, that last letter does extend the string by 1. Right? So the word ending at that node is a legitimate word. So they would see the length of that word and see if it beats the global maximum so far. But what if whether it's a leaf node or an internal node, whether if that node is not an end node, then there is nothing to do. There's no point in continuing further. So they would just return back. So we can think of this, writing this up as a base case, a recursive case, and a backtracking case where if it turns out that the partial solution so far is already an invalid partial solution, that means the last character that was added to it doesn't make sense because this node is not an end node. So we shouldn't even be going down this path. Then we can return straight away. So I'm going to write that as a backtracking case, as you might be familiar from your combinatorial enumeration class, where if the node that we are at, irrespective whether it's a leaf node or an internal node, if it is not an end node, then the path ending at this leaf node or internal node is an illegitimate path anyway. So you just return straight away. Otherwise, I could have written base case and recursive case separately. I'm going to write them together just because the work that they need to do, that needs to be done in both cases, is the same. Namely, at this point we know that they are both end nodes. So we have to take whatever has come down from this on the slate to them, right? Which means all the edge labels from the root node down to them are etched on the slate. They need to look at the length of that slate and check if that length is beating the global solution. So if the length of the slate, so let's say we have a global solution which is the longest string seen so far, which is initialized to the empty string to begin with. So if the length of the slate handed down from above is greater than the length of the global solution, then the global solution needs to be updated to be the string formed on the slate. We were also given a condition that if there is a tie, then we need to return the word that is smaller in lexicographic order. So that means there is another condition to check. Maybe they are equal. Maybe they are equal in length, but the string formed on the slate is smaller in lexicographic order than the global string.
But won't that take care of itself by the way you're traversing? So you don't have to check
So
it?
you can traverse it in a way that takes care of it. It's
You can
just that you would need to look at all the children in the order from A to
Yeah,
Z.
because the hash map is not sorted.
Yeah.
I don't.
So if you look at all the children in order from A to Z, many of them may not exist. Then yes, you don't need this second condition. But if you don't want to do that, since most of those keys may not exist, then you have to explicitly check that that the string formed on the slate. Now this is going to depend on your language, because what the slate has is basically it's a stack, so it's a sequence of characters from top to bottom up to that point, and so those sequence of characters has to be compared as a string with the global string, and if it's smaller than the global string in lexicographic order, then the global string has to be updated to be that, that string that's formed by joining together all the characters on the slate. So this is something that is to be done irrespective of whether it's an internal node or a leaf node, which is why, I could have written them separately and then joined them together, but just to save some time, we did the analysis beforehand and saw that the work done is common. Moreover, if it's an n-ary tree, we'll have a for loop that iterates through all the children. And so if there are no children, that for loop won't run. So that makes it convenient to combine the two cases into one. So we'll just have a for loop here that runs through all the children. This for loop won't run if it's a leaf node. So for every key in node dot children in the hash table, in the hash map called children, we want to delegate this work to each subordinate. How do we do that? When we make a choice, we are effectively taking the label of the character down to my child, on the edge to my child, and appending it to the slate. That's what I did in week 2 in the combinatorial enumeration class. And that's what we are doing here as well. So when we look at this character, whatever that character is, you have to imagine let me actually do the delegation first. So suppose I hire a subordinate. What will be the root node of the subtrie rooted at the subordinate? It's just going to be node dot children of key. That's the subproblem definition. The partial solution is going to be on the slate. Now this slate should have been extended because I got the slate from my manager, and so when I pass it down to my subordinate, I will need to potentially add something, append something to it. What am I going to append? The label of the character on the edge to my subordinate. So that's what I append slate dot append character. As soon as I do that, I need a slate dot pop. So that's the sandwich rule. And this for loop won't be executed if it's a leaf node. Otherwise it will be. And we are blindly hiring as many people under us as the number of children in the trie. But if any of those hires were illegitimate in that they were not the nodes at heading those subtrees were not end nodes, then that subordinate will immediately backtrack. So having done this, we will just call the helper function. So in the outer function or whatever if you might have a separate function here, but we will call going back to what we did here, we built the trie, assume that we have a helper function that is also written. We will then call the helper function, execute it as the root manager. We have to figure out what parameters we want to execute the helper function with. So as the root manager, I'm going to execute it with node equal to the root of the tree. And since there is nothing on the slate at the root node, slate is essentially a blank slate or an empty stack. Once this is executed in a top-down way, the global mailbox would have already been filled in. Whatever the value in it is, we'll just return that. Like we have done in combinatorial enumeration problems or top-down DFS problems in trees. So building the trie took time proportional to the sum of the number of characters across all the words in the dictionary. And then traversing the trie in the worst case would also take that long. So that completes the analysis also. Any questions about this? About this code? So you can see that we are doing depth first search on the trie. So we are reusing the template that we had for doing DFS on other kinds of trees, also on tries.
The data structure node dot end equal to false, you mean the children's are empty, right? Because
No, I mean that the node, whatever node I am given responsibility for, this node is not an end node.
yeah, but we don't have an variable called end in the trie node data structure, right?
No, we do. So the basic, we assume that we are working with the basic structure of a trie node, which is that it will have an end value and a hash map, children.
Oh, end value, you mean is it a word? End of a word?
Yeah, a Boolean variable which will tell us whether it marks the end of a word.
Okay, thank you.
Mohammed?
Hi, Omkar. Shouldn't we add the key to the slate before calling the helper again?
We are doing that.
Oh, we did
Yeah.
it. Okay, yeah. Okay,
Yeah.
I missed that. Okay, thank you.
Shobit.
Omkar, this join slate less than global, it won't affect the time complexity. Like in worst case, this might happen every time, right?
Yeah.
How?
Well, not. Okay. Yeah, that's true.
So then should it will
It's
become
going to be proportional to the length of the. I mean, you can't avoid it, given that.
but if it is proportional to the length of the each word, then automatically we can't say the time complexity is length of characters on the string, right?
Worst case, yeah, in the worst case, we can't say. Yeah, it will be more than that.
More than that,
Mm.
I think I have to think, but it will become quadratic, right?
Yeah,
For the summation of
d
wi.
square. D
Yeah.
square. Yeah.
So then this solution is no better than the normal brute force solution where we put all the words in set and start comparing each prefix, right?
Comparing each
Like
prefix.
just checking in the set whether every prefix is there in that set.
Oh, okay. So I see that way.
No, creating all the words once, it's twice the length of all the characters. So what? You create each word once, the maximum times. So you're just creating all the words, which is also the length of all the characters in all the words. It's the same complexity. Right? Because worst case, you'll have to just create when you traverse each word once. That takes so the complexity of that is just the sum of all the characters in all the words, which is the same complexity of the whole algorithm.
Can you elaborate on that? You're talking about the helper function, right?
I'm saying even in
complex.
the worst case, right? You have to create each word in your input dictionary once. Each word is the sum of the characters in the word. Create the words, all the words is the sum of the characters on the word, so it's the same complexity anyway. Worst case. So it's twice. You do it twice when you build the tree and when you traverse it. So I'm saying it doesn't. The worst case is the same time. Is the same.
Well, so here the issue is that when you go down a particular path, like
these are words, right? When you go down, you only do the join when it's a real word in the dictionary. You don't do it for every.
You're talking about the hash table solution or this one?
No, this one. He said the worst case you have to do these joins, right? So I'm saying that the joins just create the original dictionary. Right, so worst case, you have to create each word in the original dictionary when you traverse the tree. So the complexity of all these operations combined is the sum of the characters of all the words, which is the same complexity of the algorithm anyway.
Yes, you're right.
So Omkar, could you just repeat again, like, because I still didn't get it. Why it
should... So what he's saying is, whenever you execute this statement, see, firstly, we are executing this part of the code only when we are at an end node. Right? And when we are at an end node, that means we are looking at a word that existed in the original dictionary, in the original collection. So for that word, we are comparing that word in lexicographic order with whatever is the current best word we have seen so far.
Okay.
So that means the cost of doing this comparison can be attributed to that word in the dictionary, right? Let's assume you write down what the cost is and you tag that cost with that word in the dictionary, and then at the end of this entire DFS, if you were to add up look at all the tags, the total cost on them is not going to exceed the cost of the sum of the lengths of all the words in the original dictionary.
Okay. Maybe I'll think later on. I don't want to spend but at least with the basic recursion technique, we are trying, in a base case, we are trying to do.
So think of it this way. This will happen at most once for each.
Are you writing something?
Yeah.
Oh.
So So this will happen, this so this statement which you pointed to is going to be executed at most once for each word in the dictionary.
Yes.
Right? It's not going to be executed as many times as the number of. So I think the way you were looking at it, and that also led me to look at it in the same way, is that this will happen once for every node in the trie, potentially in the worst case.
Oh, I see. Okay.
Right?
Hmm.
Which could be true. Which could be true, but in that case, the number of words in the dictionary is also the same.
Yes. Yes.
So in which case the cost actually isn't that bad. It's no worse than the cost of parsing the entire dictionary one more time.
Oh, I see. Okay. Yeah. Okay.
Was it Tal who said this or Mohammed? Sorry, I couldn't follow the.
Yeah, that's interesting. Yeah, thanks.
Yeah. Of course.
Tal?
Yeah.
Okay. Yeah. Thanks.
Yeah, this
Yeah.
was,
So that's correct. So
Yeah.
this is. So the complexity is actually still better.
still down. Yeah, still. Okay. Thanks.
So, Omkar, just one question on join. Why did we need to join there? Because slate and global were anyway strings, right?
So slate is like an array of characters it's like a stack, so that you
Okay.
can append and pop. You can
I
push
see.
and pop from one end in constant time. That's the assumption here. And
Got it.
since you can't do that with strings, we're assuming it's an array of characters, dynamically resizable, if you want to think of its
Yeah, you
implementation.
could do pushback and pop back also in a string. Anyway, it's language specific.
Yeah. So as long as it's doable in constant time, but the comparison will still need to be.
It still need to be. Yeah.
Like you can have global instead of a string. You can have it as an array of characters, but still you would need to compare them from left to right,
Makes sense.
which is smaller in lexicographic order.
So just for Python, if you compare two strings, they will with the less than operator, it will tell you whether like in lexicographical order whether it's
Yeah.
a small.
Yeah. Okay. Let's take a break since
Sorry, Omkar, one last question. If you go to the the previous code, the way you are creating the trie, why did we need the root dot and equal to true?
Oh, that's just because the empty string itself is a prefix of every word. So we said that everything from the top, we are searching for a sort of like a contour, so that everything within this yellow region consists
Right.
purely of end nodes.
Got it.
But
If-
the root node itself is not an end node, so we don't want to handle it as a separate edge case in this code. So by just marking it as also an end node, we don't have to worry about it as an edge case.
Could you go back to the code again? So here for the prefixes, I don't see you initializing that end attribute for the internal nodes. Are you?
For internal nodes, we don't need it, but every time we complete the insertion of a word in the dictionary, we mark the node we ended with as an end node.
In that case, you could also avoid the root node and consider it as the internal node as well, right? All it matters is the leaf node where it ends, whether it ends or not, isn't it? Because
So
I don't see how you are using the root dot end attribute.
We're not using it here, but we would have to treat the root separately if we didn't mark it as true there, because the backtracking case would actually return immediately from the root node, since if it was, when we start the execution of this
Got
piece
it.
of
Yeah.
code from the root, it will immediately return, since the root itself is not an end node
Yeah, thank
by
you.
default. And plus, that's what we are supposed to return. We are supposed to return an empty string if every single child of the root is not an end node,
Right.
then we are supposed to return the empty string. So conceptually, we can think of the root node as mapping to the empty string. Okay, so, Tal,
Just a question. So if we move the if check to the for loop, then I don't need to mark the root node as an end string, right?
if I move this if check, you mean?
No. I don't do the backtracking case, so I'll check. I won't go into a child if it's
Yeah.
not
So
a node, and then I don't need to mark it because the global
Right.
starts with empty string anyway.
Right. Yeah. So the other way of implementing backtracking is for the parent to make that, well, manager to make that check before delegating to the subordinate. So yeah, in that case, if the root manager is making that check, the root manager is always going to be executing. But yeah. So that would also work. Jojan?
So in the global equal to empty string join slate, why don't you just assume global is equal to slate then?
Because the slate is mutable, it will keep changing. So we can't. We have to take a snapshot of it and make global equal to that. Otherwise, the slate it's a mutable structure.
But we are not okay. So the slate is passed by reference, right?
Yeah, it's passed by reference and it's changing. So at the initially it was empty. At the end, it's going to be empty. So
okay, if I were to pass a slate by value, then I should just assign it, right?
Yeah, but then you'll.
Then I will lose the append, right?
Yeah, but you will end up using more space in the call stack then, because every time you pass by value, you have to copy a.
Okay,
you have to create a copy.
In the constructor of the node, we are supposed to initialize a node as false, right?
Yeah. So the default value is false in the constructor, and the default initialization of the hash map is an empty dictionary in the constructor.
Okay, thank you.
So let's take a 10-minute break. It's 3:21. We'll resume at 3:30 Pacific time.
Want to become a software engineer at Google? You can, like thousands of our students. You just need to learn from those who've already cleared Faang interviews. At Interview Kickstart, our interview prep courses are developed and taught live by 150 plus instructors from Tier 1 companies like Google and Facebook. Our courses are tailored to help you crack software engineering domain interviews, including back-end, full stack, machine learning, embedded systems, data science, and more. To learn more, book your free webinar slot today